In today's lecture, we are going to take a break from neural network theory and talk about PyTorch. The aim of introducing PyTorch is so that you have an option of implementing neural networks using PyTorch. We will see an introduction to PyTorch. We will try to develop a mental model of what PyTorch is, what are its salient features, and why you might want to use it. We will also see what tensors and variables are, and these are very important concepts. We will also see how PyTorch and Numpy can work together. Then we will see how to handle datasets, and we'll also see how we can load popular and famous datasets in PyTorch very easily using the utilities. So let's begin. Let's take a look at PyTorch, the framework, and the various salient features which make it so special in this community. This is how the PyTorch website describes this framework. It's a Python-based scientific computing package targeted at two use cases. It's a replacement for Numpy if you want to run your computations on GPUs. It's also a deep learning research platform that provides maximum flexibility and speed. Let's break it down. PyTorch is a Python-based framework. It's a rewrite of the Torch framework, which was implemented in Lua. Now Lua lacked a good ecosystem and a standard library. So choosing Python, the developers of PyTorch lowered the barrier to entry, given Python's popularity. PyTorch was optimized for speed, and parts of the framework critical for performance were implemented in C or C++. PyTorch also provides Numpy-like capabilities. It's a good replacement for Numpy. PyTorch tensor model was inspired by numpy.nd array. PyTorch supports Numpy integration, as a result of which Numpy arrays and PyTorch tensors can't interoperate. But the real advantage is that tensors can operate on GPUs as well. That makes it a good reason to choose PyTorch over Numpy. For example, PyTorch is a very easy to use deep learning framework. It allows you to do faster prototyping and experimentation. It comes with a bunch of modules to build and train models, catering to use cases in areas like vision, speech, and text. For example, it comes with an automatic differentiation engine, a bunch of pre-built neural network constructs like convolutions and LSTMs, optimizers, and loss functions. We'll be digging much deeper into these various aspects shortly. But now, let's look at the salient features of PyTorch, which makes it a popular framework in the community. So, PyTorch is deeply integrated into Python. All PyTorch computations run within the Python runtime. This is unlike frameworks like TensorFlow, where Python is used to declare the model and then compiled into an intermediate optimized representation to be executed on a virtual machine. PyTorch is imperative just like Python. That means that statements get executed as soon as you execute them, instead of being executed later once the entire workflow is known. An example in the next slide will make this clear. PyTorch can be extended just like you would extend Python. Writing new neural network modules or interfacing with PyTorch Tensor API was designed to be straightforward and with minimal abstraction. PyTorch uses a dynamic computation graph. Now all deep learning frameworks are computation graph toolkits. That means that workflow is structured in the form of a graph and then executed. But some frameworks are dynamic or imperative in nature, while some are static or declarative in nature. PyTorch is dynamic, while TensorFlow is static. To understand the difference between these two approaches, consider how you would write a high-level program in C and in Python. In C, you would write the entire program, compile it, and then execute it. This makes the program static or declarative. You are declaring everything before executing it. Whereas with Python, you can execute pieces of the program as you declare them, with no demarcation between declaration and execution. PyTorch that way is dynamic or imperative, in the sense that the computation graph gets built as statements get executed. This has several advantages, especially in cases where the model depends on the input structure, which can be dynamic. PyTorch has a very intuitive programming model. PyTorch follows a define and run model. That means you don't have to build the entire computation graph before executing it. You can execute it as you define it. This makes it very convenient for faster prototyping and experimentation. You can keep a very linear thought process while building your model, which is very convenient. It is easier to debug in PyTorch. PyTorch doesn't use a separate virtual environment, unlike, for example, TensorFlow. Since PyTorch uses Python execution environment, debugging is very easy. You can use same debuggers that you would use for Python. The stack trace would give you the exact line of error, which speeds up your development process. Next, we are going to mainly look at tensors and variable structures. But before we do that, we are going to do a quick refresh on a few concepts, namely scalar, vector, matrix, tensor, rank, and dimension. These are important while handling tensors. Then we are going to learn about tensors and we are going to do a hands-on session with it. Then we are going to do a refresher on differentiation and the computation graph. These are important in order to understand what the variable data structure does. Then we are going to learn about variables and do a hands-on session with it. So here's the refresher on some of the terms, which might help you appreciate tensors better and will be handy when you use these tensors. So scalars are simply single numbers. They are dimensionless. They can be real numbers like 1.2 or natural numbers like 3. The rank is always 0. A vector is an ordered array of single numbers. They have a rank of 1. The rank suggests how many indexes you need to locate a single element in that structure. In the case of a vector, you just need one index. The dimension of a given vector on screen is 3. It has 3 elements. Note that sometimes the term dimension is used synonymously with rank, so you have to derive it from the context. Matrices are rectangular arrays consisting of single numbers. They always have a rank of 2, suggesting that you need 2 indexes to locate a single element in that structure. The shown matrix on screen has a dimension of 2, 3, which means it has 2 rows and 3 columns. Moving on to tensor. Tensor is a general term used to describe all these structures, but more specifically for a rank of 0, 1 and 2, they are called scalar, vector and matrix. Anything beyond 3 is called a tensor. On the screen you have an example of a tensor which has a dimension of 2, 2, 3 and a rank of 3. You can derive from this that the rank is nothing but the length of the dimension. Next, let us visit tensors in PyTorch. These are data structures. They are multidimensional matrix containing elements of a single data type. They are part of the torch package and we will see that when we do a hands-on. They are instantiated via torch.tensor group of classes. They are grouped based on the data types that they may store. They can be created and stored on either CPU or the GPU. There are a number of operations that can be applied on tensors, which we will see in the hands-on session. And most importantly, their design is inspired from Numpy arrays. This means they are interoperable with Numpy arrays, which we will also see in the demo. There is an example shown on the screen where we are creating a tensor of dimension 2, 3 of type float. Depending on your need, you might want to instantiate tensors of certain data types. As we will see in the deep learning sections, most of the time we'll be using float. But you also have access to tensors of various data types like double, byte, char and int. So here's the handy chart. Now let us proceed to do some hands-on coding with tensors. So in this section, we'll do two things. We'll take a look at creation of tensors and we'll look at the operations that you can do on these tensors. An important package to do all this is the torch package. In cell 1, let's import the torch package and it contains all the necessary data structures to create these multidimensional tensors. And it also defines all the mathematical operations that you can do on them. Coming to cell 2, let's print the version of PyTorch that we are using today. so it happens to be 1.7.1. Now in cell 3, let's start by creating some tensors by using the torch.tensor class by passing the arguments 2 and 3, and this will create a 2 by 3 matrix, a matrix with 2 rows and 3 columns. Let's print it out. Here you can see that we have a matrix with 2 rows and 3 columns, but interestingly its data type is float.tensor. So tensor is an alias of float.tensor. So the above was almost equivalent to using float.tensor class directly. Do not assume anything about the values these elements take. They are all undefined and indeterminate. Now in cell 5, you can inspect each of the elements by using indexes. As we saw earlier, for a matrix, you need 2 indexes to get the value of that element. So in this case, we are typing the type of the element, which is float. So in cell 6, you can also go ahead and inspect the element itself. Now in cell 7, let us look at the dimensions and the size. We had specified a 2 by 3 matrix, and that's what we got with the size method. And the dim method here returns 2, which is actually the rank of the matrix. And of course, we discussed this earlier, the length of the size will be equal to the dimension always. Now you can set values into the tensor by using the indexes. So here in cell 8, I am specifying values from 1 to 6 for all the elements. This is how you will cast a tensor of one type to another. So for example, in this case, we create a float tensor. In cell 9, we type it, and then we converted it to int by using the type method. So as you can see here, this was originally a float tensor, now converted to an int tensor. We lose the precision, obviously. Now let us explore some more ways of creating a tensor. So moving on to cell 10, you can create one tensor from another like this. In cell 11, you can create a tensor from a Python list. In this case, this is 2-dimensional and the data type we specified is an int. So this gives us an int tensor of size 2 by 2. In cell 12, we can also create a tensor from Numpy Array. So in this case, we are creating a Numpy Array. It's a vector, and then we are passing it to tensor to create T4, which becomes a float tensor of size 2. Then in cell 13, we can create tensors with all zeros by specifying their dimensions. For example, to create a 2 by 3 tensor with all zeros, we can make use of the zeros function. In cell 14, we can do the same with ones. And lastly, in cell 15, you can create one tensor from another just by using its dimensions by populating every element with ones. You can also do this with zeros. Next, let's take a look at the various operations you can do on a tensor. Of course, this is not an exhaustive list, but here are some examples. So, the way we add two tensors would be using the plus operator. So, here in cell 16, we are creating two tensors of all ones with dimensions of 2 by 2, and then we are adding them. So, as expected, they all have an element value of 2. Of course, the operation was not stored anywhere. We could have stored this value in a tensor and printed it. There are a couple of concepts that you have to know while using these methods. The concept of in-place and out-of-place operations. In cell 17, when you do t1.add t2, the value of t2 gets added to t1, but none of the tensors t1 or t2 gets altered. It creates a new tensor which can be captured like so. So as you can see, the value of t1 did not alter here. There's all ones, whereas the addition gives us 2. But there is a convention followed in PyTorch where any operation suffixed with an underscore does an in-place operation, which means this will actually alter the value of t1. So let's see that. So now in cell 19, when we add using a suffix underscore, and in cell 20, when we print t1, we see that it's all 2's, which means t1 was altered. The other thing is that there are operations that you can either do on the tensor as a method, or you can invoke the functions available in the torch library to do the same, like so. So here are a few more operations that might be interesting to you. Now coming here to cell 23, the Linspace function creates a one-dimensional tensor of steps equally spaced between start and end, with a step size as mentioned. In cell 24, the arrange function gives you a 1D tensor with values from start to end, excluding the end, with a step size of 1. In cell 25, the rand function generates a random Legion initialized tensor with a dimension specified here. The rand function samples from a uniform distribution, and if you want it to be sampled from a normal distribution, you can go with rand n as shown in cell number 26. Lastly, here is something that we'll be doing more often in deep learning, which is matrix multiplication. So in cell number 27, here I am creating two tensors, the first one with a dimension of 2 by 3 and the second one with a dimension of 3 by 2, and then we are doing the matrix multiplication on them, like so. There are many more operations like 200 plus. Here's a link to the page where you can browse all of them, and I encourage you to try them, whichever comes out interesting to you. Now before we explore variables in PyTorch, let's take a look at the concept of differentiation and that of computation graph. Most of what we will learn about these topics won't be directly used during PyTorch programming. The framework is going to take care of it under the hood, but it might be useful to know some of these concepts in case you want to go deeper at a later date. Now, differentiation or differential calculus deals with the rate of change between two quantities. For example, if y is related to x via the formula y is equal to 2x, it is easy to see that if we make a small change in x, the resulting change in y will be twice the change in x. In other words, the ratio of change in y, which is dy, to the change in x, which is dx, would be 2. This concept helps us to realize how a change in an input x would result in a change in the output y. Given the relationship between y and x, we can call the function f to be our model and the value 2 to be the model parameter. In machine learning or deep learning, x and y are given in the form of data, and our purpose is to find the appropriate model f and its proper parameter values, like 2 in this case. This would be able to reflect the relationship between x and y in the data. Differential calculus helps us achieve just that. X can be, for example, the pixels in an image, which is the input, while y can be the class value of that image, which is the output. X can be text in one language and y can be text in another language. This is the core concept that drives backpropagation, which is the algorithm to find effect of changes in the model parameters to that of the output. The output is usually the loss, which signifies how badly we are doing in mapping the inputs to the desired outputs. Note that output y might be dependent on multiple inputs x1 to xn. In that case, we would like to know the output changes with respect to each of these inputs. In fact, we would like to know how the output would change with respect to any of the model parameters, which would then help us tune the model parameters properly to reflect input-output relationship in the data. The vector dy by dx1, dy by dx2, and so on is called the gradient of y with respect to x. Here's a table of differentiation for various functions. You might have seen this in your school days. The next concept that we should understand is that of the computation graph. It is a graph to weave variables and operations on those variables together. For example, given the equation on the left, it can be expressed as a graph as seen on the right. The input nodes suggest the input variables, and each node suggests the operations performed on its input. Now, why is this useful? Neural nets are expressed in this way, and by using differential calculus and back propagation, we get to train the model on desired input-output characteristics of the problem. Input can be an image and output can be its class. For example, input can be an image and output can be its class. PyTorch has dynamic computation graphs, where the graph gets built as the instructions are read. This is in contrast to, for example, TensorFlow, which uses static computation graphs, where the entire graph is expressed first and then it is compiled and optimized and executed. In this example, WH, H, WX and X are inputs to our computation graph. They pass through various operations like matrix multiplication, add and tanh, ultimately resulting in next H, the output. Given this graph, we would like to know who the parent of a node is or what would be the gradient of the output with respect to one of the inputs. The question is, how do we model these nodes? This is where the concept of variable comes in. They are crucial data structures in PyTorch and they are created via the torch.autograd package. They primarily wrap three things. They hold a tensor as a data member, they also hold the parent function which created this tensor, and they hold the gradient of the output with respect to the tensor. They are important when we train a model. Going back, when we have next h as the output, by calling the backward method on it, we are able to compute the gradients of the output with respect to all the units. This is very essential for training a model. Next, let's see variables in action in this notebook. Let's explore variables. In cell 1, we start off by importing torch and then we import variable from torch.autograd package as we saw earlier. Then we go on to create a small computation graph. In cell 2, first we create our input x as a variable which will hold a tensor, a float tensor, and we also specify this flag called required_grad is equal to true, suggesting that we need to find the gradient of the output with respect to this tensor. Then we create y is equal to twice of x and consider y to be the output. Now in cell 3, let's print out x and y and we see the values here, and these are as expected. But now you must remember here that x and y are not tensors but variables. The tensors are held in a member called .data, which you can see here in cell 4. They also hold the function which created them. So in this case, in cell 5, x.grad function would be none because it was provided by the user, whereas y.grad underscore function suggests that it was multiplication operation that created it. Now in cell 6, if we call the y.backward method, the autograd package finds the gradients of all the inputs with respect to y, which is the output. Now in cell 7, we can investigate these gradients. It is 2 for x, which was as expected, and now we will move on to see the working with PyTorch and Numpy. Now let's take a look at the interoperability between PyTorch tensors and Numpy arrays. Now we have been using torch.tensor for a bit now, but it is interesting to note that it was modeled around Numpy in the arrays. This actually led to lowering of the learning curve for people who were already familiar with Numpy. Now the APIs are not an exact match, but they are very similar. PyTorch supports more than 200 operations similar to Numpy. The memory pointers are shared between PyTorch tensor and Numpy in the array, making conversions extremely fast with zero memory copy overhead. This is a two-layer neural network implementation using Numpy on the left and PyTorch on the right. They look very similar due to the similarity between tensor model and in the array model. You are not supposed to be able to read the code, but from the structure you can derive that these are quite similar. Now let us take a look at the interoperability between tensors and Numpy in this notebook. So in cell 1, firstly we import torch and Numpy, and then we are going to see a few operations that we can do to interoperate between a Numpy and tensor. So coming here to cell 2, in the first operation that we are going to see, we create a Numpy array and then create a torch.tensor using that Numpy array. So we do that by creating the array first, and then we use from_numpy function to convert this np.array into a tensor. So as you can see here, this is the np array and this is our torch tensor. An interesting thing to note here is that their memory is shared, which means now if I change an element in np.array, it gets reflected in the tensor like so. So here in cell 3, I changed the first element, I updated its value to 100, and now I can see that the change is reflected in torch tensor. Now let's do it other way around in cell 4. Let's create a tensor and then extract the np.array out of it using the number method of any tensor. And as with the previous case, in cell 5, let's make a change in the tensor and it gets reflected into the np.array like so. So now we will move on to see working with PyTorch and GPU. Now let's visit some of the important concepts in handling data, namely dataset, epoch, batch and iteration. Then we will see more on how to access popular datasets via the Torch Vision package. So let's begin. A dataset is a collection of training examples. This can be, for example, a corpus of images to train the model to classify cats from dogs. Epoch is one pass of the entire dataset through your model during the training. Of course, this may not necessarily mean that you take the entire dataset through your model in one shot. That might not be possible due to memory constraints, and it's also not recommended. The dataset is broken down into batches. A batch is a subset of the training examples passed through your model at a time. An iteration is a single pass of one batch. A single pass means giving your data as input to the computation graph, performing all the iterations, performing all the operations through the graph, ending up with a loss function, and then propagating that loss back through the graph till the inputs to train the parameters. Let's see an example. Let's say you have a dataset of 1000 images and you will need to train your model. One epoch means that your model will have seen all the images, that is all the 1000 images. But then, as we have discussed, you won't be passing all these 1000 images in one shot. You will be breaking them into batches, or rather mini batches. With a batch size of 50, you will need 20 iterations to pass all these images through your model. 20 comes from 1000 divided by 50. So now we are going to see how to run tensor operations on GPU. Now if you don't have a GPU, I encourage you to make use of Google Colab by going onto this link, and I have provided the instructions over here, and you can just run this notebook over there. Now in order to demonstrate this, we will jump right into this notebook. So before we proceed, here is a note on the terms. When I say tensor on the CPU or data on the CPU, I mean data in the system RAM accessed by the CPU. And when I say tensor or data on the GPU, I mean data in the GPU RAM accessed by the graphics processor. So in cell 1, the first thing we do is import the Torch package. An important package in the PyTorch ecosystem is torch.cuda, which contains all the infrastructure to set up and run GPU operations. So the first thing we'll do is interrogate the system and see if we have access to a GPU. So in cell 2, we can do that by invoking the is_available function. It returns a true if we can make use of a GPU attached to the system. Now note that simply having a card attached is not enough. You also need to have the CUDA environment set up. The next thing we'd like to see is how many cards we have attached. So in cell 3, we do that by calling the device_count function. In a multi-GPU environment, this count will obviously reflect the number of cards you have, and all of them are accessed by a zero-based index. So in cell 4, for example, you can get the name of the first device by calling get_device_name and passing in an index of 0. So here we see that I have only one card, and that's Tesla T4. Next, we'll do some tensor operations, and we'll create tensors on CPU and switch them to GPU and back. So to do that, in cell 5, let's create a tensor using torch.float tensor, which creates the tensor by default on the CPU. In cell number 6, let's print it out. Now, in order to move this tensor to the GPU, in cell 7, we invoke the CUDA method and pass the GPU index ID. And note that this is 0 by default. So, if you have just one card, you can skip mentioning the 0. So now, if we print T, you will notice that it is now torch.cuda.float tensor, suggesting that it has been transferred to the GPU. Now, in cell 8, we can directly create this tensor on the GPU by actually using torch.cuda.float tensor, and we give the dimensions here. So now, in order to switch it back to the CPU in cell 9, we have to invoke the CPU method, and this will bring it back to the CPU as suggested by its type. Another thing that is quite handy to use is the device context, especially when you have multiple GPUs. For example, in this case, in cell number 10, by setting a device context with a device ID of 0, all of the tensors created within it or underneath it will be created on your first GPU like so. We can also shift the entire modules to the GPU and back. So we will see examples of these use cases when we go deep into the later models. Now we will move on to handling datasets in PyTorch. Now let's do some hands-on coding and see how to load datasets in PyTorch, specifically for vision use cases. Talking about datasets for classification use cases, where you've been given an image and you have to classify its class, you would have a corpus of images, and for each image the correct class label. For other use cases, the labels will have extended information. For example, for object detection, the labels will have bounding box coordinates for the object in the image, along with the object class. In this exercise, along with the object classes, in this exercise, we will load the CIFAR10 dataset and iterate through it. The CIFAR10 dataset consists of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. There are 50,000 training images and 10,000 test images. It's a very popular dataset and it's used for image classification. If you had to start from scratch, you would have to write down your own mechanism to load this dataset and iterate through it. The Torch Vision package makes it easy for you. It consists of popular datasets like CIFAR10, model architectures, and common image transformations for computer vision. In cell 1, the first thing we do is import some of these necessary modules. Next, let's talk about transformations. They are applied to each image. Some of them are mandatory, like converting the image to a tensor and normalizing the image. They are mostly used in CNNs, so we are not going to cover them in detail. But just know that they can be set in a pipeline and chained together, as you can see in cell number 2. The composition can then be supplied to a dataset. Then we have a dataset class that is an abstract class. It represents the data that you have on your hard drive. Now all datasets like the CIFAR10, which is made available to you, are inherited from this dataset abstract class. It also represents the dataset on your file system, and via the len and iter functions, it allows its clients to iterate through this dataset. Custom implementations would read custom datasets and provide the standard interfaces to its clients. So, in cell number 3, the CIFAR10 class did the work for us in loading the dataset. This class has mechanisms to download the dataset from source, unpack it, and provide us with the necessary iterators. It takes 4 arguments: the location where the data needs to be downloaded, whether you need the training dataset or the testing dataset, should it download the data or not, and the transformations that need to be applied to each image when asked for. And so it then downloaded the dataset. In cell 4, Let's see how many training data points we have. So we have 50,000 as was expected. Now coming to cell 5, let's see what an image looks like in this dataset. So we can index it into the data member variable. There is also a targets variable which has the corresponding class label for each image. The images are very small, but here we can make out that this is an image of a truck, and class ID number 9 happens to suggest the same. The class labels can be referred to from the CIFAR 10 main site. Now let's take a look at the data loaders. Now data loaders are used to load multiple samples in parallel. It provides an iterator to fetch one batch at a time with the batch as specified. Now it helps in three things. It helps in fetching batches of data, and it does this by reading from the test set that we mentioned before. It also has the ability to shuffle the data, and it can also hold the data in parallel using multiprocessing workers. So in cell number 6, you can create a data loader like so by passing the dataset, the batch size required, whether it should shuffle the data or not, and the number of workers it should use to load the data in parallel. Now that we have our dataset and data loader ready, let's take a look at a sample training loop. So in cell number 7, in the training loop, you would iterate through your data loader, which will give you one batch at a time. Each batch will have the image data and the corresponding labels. The batch size will of course match the batch size you had specified while creating the data loader. Here we are printing some useful statistics for each iteration. We are breaking out of the first iteration because this is for demonstration purposes only. Here we would have trained our model. So here we see that we did one iteration. The data or the tensor containing all of our images was a float tensor. It had 10 images. Each image had 3 channels, and each image was 32 by 32 pixels. The labels, on the other hand, were torch tensors, and we had 10 of them, which match the batch size. The labels would index into the classes, suggesting the correct class. Okay, so that's how you would load and iterate through your dataset. Now moving on, if the dataset that you need is not provided by the Torch Vision package, you would have to create your own dataset and read your own data. And you will do that by creating a custom dataset class, which inherits from torch.utils.data.dataset. And you will override the length and iter function and provide your own functionality. Once done, you can use the data loader class to iterate through this and provide the batching and shuffling functionality to your training loop. So that concludes the section on handling datasets. Now let's see some use cases where we can use PyTorch to solve deep learning problems. The two categories of use cases that I am going to highlight here are drawn from the ability of computers to make sense of visual data and language. Language either in the form of text or speech. Computer vision allows a computer to make a sense of pixel information and extract meaning out of it. The simplest and the most used use case is that of image classification, which is the ability of a vision system to correctly categorize a given image and call out its label, in this case a cat. While doing so, if it is able to locate the object and drop bounding boxes as well, we call it localization. Object detection is the ability of a vision system to identify multiple classes of objects in an image, and it's also used to locate them by drawing bounding boxes around them. In this case, it has identified a cat, a dog, and a duck. Things can get more challenging in instances like segmentation, where the system is able to do classification at a pixel level. It not only segments the image pixels into parts of the image, but also classifies each part into one of the predetermined classes. Now let's turn our attention to natural language processing. Natural language processing is concerned with interaction between computers and humans using natural language, and in particular, it is concerned with programming of computers to fruitfully process large natural data. A couple of very useful tasks are sentiment analysis and machine translation. Sentiment analysis usually takes in subjective data in the form of text, like online reviews and feedback, and tries to determine the sentiment in it. It can be used to know if the opinion was favorable or not, whether it was a good or a bad review, for example. Machine translation is the task of automatically converting one natural language into another, preserving the meaning of input text and producing fluent text in the output language. If you have used Google Translate, for example, you have used this technology. Now, PyTorch, via its various packages and utilities, allows us to apply deep learning techniques to complex data. We already saw the torch package, which gave us tensors, and we also saw the torch.autograd package, which gives us variables. But that was just the surface of it. We will go into the details of each package as and when we use them shortly. So moving forward, we will be training our neural network, and the purpose of this section is to get into the basics with the help of a simple neural network. We will also briefly look at the concepts like nodes, weights, biases, and activation functions, and we'll see how they come together. Lastly, we'll look at model training and inferencing. So first, we'll build an artificial neural network, and in that process, we will revisit concepts like nodes, weights, biases, activation functions, and how they come together. Then, we'll take a look at the loss functions, which help us know if our model is being tuned in the right direction or not. A higher loss value would obviously mean that we are moving away from where the correct model weights should be. Then we will learn about optimizers, which help us tune the model rates properly, and it does so with the help of gradients calculated on the loss with respect to all the weights and biases. Once our model is ready with the loss function and optimizer in place, we will proceed to train it, and once trained, we will do inferencing on unseen data. We'll also see how to save this model to disk and load it back. And for those with the GPUs, we'll tweak the model to run all the computation, all the training on the GPU. So let's get started. So we have already seen the motivation behind creating a neural network. A neural network, also called an artificial neural network, is actually a graph data structure. It has nodes and edges. The nodes with their incoming edges are called artificial neurons with respect to the brain component from which this is partially inspired. So to understand neural networks, it's best to start by understanding a neuron. It's actually a mathematical equation but conveniently visualized as shown. It is characterized by a node, the circle with incoming edges, and an outgoing edge. Each incoming edge has a weight associated with it. The node itself has a bias associated with it. Each incoming input gets multiplied by the edge weights, and then the value gets added to the bias. In a sense, we are calculating the weighted sum of the inputs, and the resultant output can take any value from negative to positive. It is then passed through what is called an activation function, which is very important, and that output becomes the output of the total neuron. So that's the composition of a neuron. When we say that we are training a neural network, all we are doing is tuning the values of these weights and biases which we have no idea of when we start training it, so that we can achieve a desired input-output relationship. The desired input-output relationship is given by our training dataset. The weights, as you can imagine, suggest what is the relative importance of each of the incoming inputs, and the bias suggests the output of the neuron independent of the inputs. For example, it is the value the neuron will emit when all the inputs are 0. Now let's take a look at activation functions. They are a very important component of neural networks. It is due to them that the network is able to learn complex boundaries in our dataset. They bring non-linearity into the network. They decide when the neuron should fire or have a value something other than 0. Now without these functions, the model can only dissect the dataset with linear lines because all the calculations together become one large linear equation without these functions. With the activation functions, the network can partition the data with complex boundaries and can do useful tasks. Here are some activation functions and their input-output characteristics. The sigmoid takes its input and squashes it between 0 and 1. When the input is near to 0, the output has the nice gradient. Whereas if the input tends to be negative or positive, the output saturates to 0 or 1. Tan H does the same thing, but in this case, the output changes from -1 to +1. ReLU, in that sense, is very simple. If the input is 0 or less, the output would be 0, and for every other case, the output would be the same as the input. Almost all of the deep learning models use ReLU, which have given good results for a variety of tasks. A neural network is constructed by joining together neurons that we saw earlier. The neurons are segmented into an input layer and output layer, and one or more hidden layers. So here we have a multi-layer feed-forward neural network. A user of the neural network gets to interact with the input and output layers. The input can be, for example, pixels from an image, and the output can be the class of the image. Any given layer will have incoming connections and outgoing connections. For example, in this case, the hidden layer gets 3 incoming edges per node and has 4 outgoing edges. Also, the output of the neural network can be given to a classifier for classification. Okay, so with that knowledge, let us proceed to build an artificial neural network and inspect its elements. And so, for that we will jump right into a demo. So, in this section, we'll be building a fully connected feed-forward neural network to classify a flower based on its structural attributes. In cell 1, we start by importing all the modules that we need. Now, in order to access the dataset, which is in the form of comma-separated variables, I have written a small module and created a PyTorch dataset. You can take a look at this in cell 1 if you are interested in knowing how that was done. Now, when working with any of the neural network code libraries, TensorFlow, Keras, CNTK, PyTorch, you must write code to serve up batches. Of training items. This is a surprisingly annoying and time-consuming task. When you can load all training and test data into memory as a Numpy array of array style matrix, then you can write a custom batcher class that will serve up indices into the data. This isn't too difficult, but when your data is too big to fit into the memory, you have to write buffering code to read chunks at a time from the file. The PyTorch library has a mechanism to help out. Here, I have coded a custom iris dataset class that has 3 methods: init, getItem, and len. The getItem method must be coded to return a data item at the index. After implementing the custom dataset class, you instantiate objects and pass them into the built-in data loader class. A data loader object can serve up batches. Well, we are not going to go into much details about this as it's not that important. So, the dataset that we are talking about, the iris dataset, which is quite popular in machine learning, has 4 attributes. So, these attributes of the flower iris are called, and you have worked with this dataset before. So, the 4 attributes are sepal length, sepal width, petal length, and petal width, along with the class of the flower. A sepal is the part of the flower bending downwards, like this one, whereas a petal is the one which is standing upright. These attributes map to one of the 3 kinds of flowers found: the iris setosa, the iris versicolor, and iris virginica. The challenge is to create a model which, when given the attributes of the flower, should classify it into one of these 3 classes. Here are some examples. Now, in cell 2, let us read the dataset and let us read the first few lines of the dataset and see what it looks like. So here we see the 4 columns of the structural attributes and the class of the flower. With that dataset and challenge in mind, Now let's create a fully connected 3-layer neural network. So coming to cell 3, the choice of the number of layers and the number of nodes per layer is part of the design process of building a neural network. You might have to try a few variations to see which fits best given the dataset you have. All the neural networks in PyTorch are built by creating custom modules, which are classes inheriting from the nn.module base class. The advantage of this is that modules can be nested within each other like a tree structure, and so you can group different groups of layers together and keep them logically separate. The two methods that need to be implemented here are the init method and forward method. The init method gets called when you instantiate this class. It is used to create the various layers, create activation functions, initialize stuff, and so on. So in this case, we are taking 4 inputs. The input size is the number of attributes of the flower, and it will be used to create our first fully connected layer. The next two parameters, hidden 1 size and hidden 2 size, suggest the number of nodes that you want to have in the hidden layers. The higher the number, the better the model can fit the training data. But too high of a number can often lead to overfitting, a problem where the model learns the training data so well that it performs poorly on the unseen data. The num classes parameter will be the number of classes we have in the dataset, which happens to be 3. There are also the number of neurons we want to have in the output layer. Hence, these 3 neurons on the output layer will give our 3 class scores, 1 for each class. If the model is properly trained, the class with the highest score should match the actual class for that data instance. So, in the body, we are creating 3 linear units, and these 3 are the classes which implement fully connected layers. They take 2 arguments, the number of incoming edges and the number of outgoing edges. They also create 1 bias per number of outgoing edges. Also, we are creating 2 ReLU activation functions to go with the first 2 hidden units. The last one, which is FC3, will be our output layer, which will output the 3 class scores. Then we have the forward method. The forward method is where you combine all these together. The forward function is called with inputs to the module. In our case, the attributes of the flower, and it returns the results of the calculations, which are the class scores. In this case, first we are passing the input through a fully connected layer, followed by our ReLU activation function, and this constitutes our first hidden layer. We do the same with our second hidden layer, and finally the output is passed through the output layer, giving us the class scores. Hence, in go the attributes of the flower and out comes the class scores. Also note that we always process data in batches. What we'll be passing in here are a number of instances as a batch, and the output will be a set of class scores for the entire batch. The number of data instances in the batch is governed by the batch size, which is set while iterating through our dataset. So now here in cell 4, you can actually print all the layers from an object of this class, like this. So in this case, we instantiated IrisNet with 4 as the input size and 3 as the num classes, and we have chosen 100 to be the number of nodes in the first hidden layer and 50 to be the number of nodes in the second hidden layer. The description printed here suggests everything that we have discussed. Next, in cell 5, we will be creating the data loader. We select a batch size of 60, suggesting that in each iteration, the data loader will give us 60 instances. So, if the total number of instances in the training set is 120, we have 2 iterations to cover the entire set, which is actually 1 epoch. We also have the iris data file in text format, which contains comma-separated values that we are interested in. So, in cell 6, the first thing we do is we create the datasets by calling the getDatasets function. Remember, this is the module that I implemented in cell 1. So, what we see here is we have 120 instances in the training set and 30 instances in the testing or validation set. I'll be using these two terms interchangeably. Next, we create data loader whose responsibility is to allow us to iterate through this dataset. And there are a few things we can do with the data loader. First, we set the dataset and then we select the batch size and then we set shuffle is equal to true. The shuffle is equal to true flag indicates or instructs the data loader to have the data reshuffled at every epoch so that we get different batch compositions every epoch. Okay, so that was about creating our first neural network using PyTorch and creating the data loader. Now before seeing the rest of the code, we will first focus our attention on loss functions and optimizers. Now we are going to understand loss functions, what they are and what their importance is. And we are going to look at a specific loss function called the cross entropy loss that we will be using in the model training. So the purpose of the loss function, also known as the objective function or the cost function, is to give an indication of how good our model is doing in terms of predicting the right outputs in comparison to the actuals. It acts as a feedback mechanism and helps us in fine-tuning the weights and biases of the model. The loss function takes as input the model predictions and the actuals and gives us a loss score suggesting how good the prediction was. And during training, our objective would be to reduce this loss score. PyTorch comes with a set of predefined loss functions which are particularly used while building models and while training models. We'll be using the cross entropy loss, and you can also implement this on your own if it is not found in the list of losses as supplied by PyTorch. So to talk about cross entropy loss, it is used in scenarios where the model has to predict the right class from a set of classes. So in this example, let us say the model has to predict the class of a fruit given the input of the image of that fruit. In this example, we are showing so far a single instance from the training set. We see that the model predicts that there is an 88% chance that the image is that of a mango and the expected or actual result is a mango too. And in this case, the cross entropy loss function would give us a low loss score, suggesting that the model did really well. If the actual class was to be an apple, for example, the score would have been really high. So that's about cross entropy loss. Next, we are going to talk about optimizers in PyTorch. So before we understand optimizers in deep learning, let's talk about the optimization problem. The optimization problem is the problem of finding the best solution from all the feasible solutions given some criteria. That is when you have a lot of ways to accomplish a task, but your aim is to find the best way given some criteria. For example, at the supermarket, when you are deciding which line to stand in, you are actually solving the optimization problem. So in this case, the criteria is to spend as little time as possible in the line in the queue. So in our case, we need to find the best value for the model parameters, the weights and the biases, which would give us the desired input-output characteristics. So continuing with the block diagram we drew for the loss function. So once we have the loss score, the question is, what do we do with it? How do we update parameters of the model so that in the next iteration we can further reduce the loss? To do that, we first calculate the gradients of the loss with respect to the model parameters. This tells us which parameters have more influence on the loss and whether the influence is positive or negative. Or in other ways, does it help in decreasing the loss or increasing the loss? This gradient calculation is done by a technique called backpropagation. This information, that is the gradient, is then given to the optimizer of our choice, which then updates the model parameter values using a predetermined strategy. By updating, we mean adding or subtracting small values from the existing values of the parameters so that the loss can be further reduced. this entire cycle is one iteration. Talking about the type of optimizers that we have at our disposal, PyTorch comes with the implementation of several commonly used optimizers, and there is also a scope to build your own optimizer by extending the framework. So these are some of the most famous or the most used ones: stochastic gradient descent, adder delta, adder grad, adam, RMS prop. Optimizers take one or more parameters which affect their behavior. The most important of them is the learning rate, or the LR parameter, that you will see in this example. The learning rate tells the optimizer how big the step size should be towards the direction of the lower loss. A higher learning rate, higher than the optimal one, may not allow the optimizer to converge, while a lower learning rate may make the optimizer take too long to converge. The best learning rate is often deduced iteratively through experimentation. Here are some visualizations of various optimizers trying to get to a lower loss on two different error surfaces. An error surface is a portrayal of an error in terms of the model parameters. For example, on the right image, we have two parameters shown as the two horizontal axes, and the error is represented by the vertical axis. The role of the optimizer in this case is to find the proper values on the two horizontal axes that would reduce the error. Now this is a challenging problem and an active area of research. The performance of these various optimizers shown here are suggestive, and often a few need to be tried out to figure out which works best for your problem. So with that, let's use all the knowledge we gained in terms of neural networks, loss functions, and optimizers to train a neural network. So this part is all about how we train the artificial neural network that we have built. So let us jump directly into the notebook that we had left midway. So the last time we explored the iris dataset and we saw various attributes and classes of the dataset. We built our neural network and we created data loaders to ingest the dataset. Now we are going to train the model, but before doing that, we have to create a few more artifacts. In cell 7, the first thing we do is we instantiate our neural network from the IrisNet class that we have just created. As discussed, we pass the number of attributes as the first parameter, which will set the number of input nodes. Then we pass the number of nodes we want to have in the first hidden layer and the second hidden layer. Then we pass the number of classes, which will set the number of output nodes for this neural network. The next thing we do is we create the loss function. As we discussed earlier, we will be using the cross entropy loss. The final thing we create is the optimizer. Here we are using the stochastic gradient descent optimizer. The first parameter we'll pass is all the parameters of our neural net. So the optimizer knows what to update when it is doing the operations. The second parameter is the learning rate. We are setting a learning rate of 0.001, which dictates the size of the steps that we are going to take in the direction of lower loss. We also enable Nesterov momentum, which helps it to converge faster. The other two parameters are actually used by the Nesterov logic. So now what remains is running our training loop. Now there is a lot going on here in cell number 8. So let's go line by line. Our training loop basically consists of two loops: the outer loop that executes the epochs, while the inner loop executes the iterations per epoch. We have set a value of 500 for the number of epochs that we want to run. Remember that during each epoch, the network would have seen all the training data once. We created some lists to record how we are doing with respect to the training. Namely, we want to know the losses against our training and test datasets and the corresponding accuracies. In the inner loop, we first iterate through the data loader, which gives us one batch per iteration. This batch is a tuple. The first element is a float tensor with the attributes of the flower, and the second one is long tensor containing the actual order of true classes. We put them in variables which are essential for training, especially for calculating the gradients. Then we put the network in training mode, which allows all the functionalities like dropouts and batch norm if used. The other possible mode is eval, which is used during inference. Next, we will execute all the steps that we saw in the optimization part. Namely, we first clear off any gradients from the passed operation. Then we do a forward pass, wherein we pass our attributes through the network and get our class scores. Then we pass the class scores and the expected or the true class values to our loss function, which gives us the loss. Then we do a backward propagation or back propagation on the loss, which will calculate the gradients of the loss with respect to all the parameters. And once that's done, we ask the optimizer to adjust the parameters based on the gradients calculated. We do so by calling the step method on the optimizer. The rest of what we do in the loop is all bookkeeping. Specifically, we want to know the loss and accuracies on the train and test dataset. So in the iteration loop, we record the total number of correct predictions that we got against the total or the batch size. And outside the loop, we are recording the training loss of the last iteration, which is given by the loss variable. And also we are recording the training accuracy, which is nothing but the correct answers divided by the total items we saw. Or during training, the model never saw the testing data or the validation set. Also, we record the training accuracy, which is nothing but the correct answers divided by the total items we saw. We do the same with testing or validation dataset. Now remember that in the training loop or during training, the model never saw the testing data or the validation data. So this is an indication of how well it does with the unseen data. So for that, we access the test dataset and we extract the items and the classes or the attributes and correct labels. We pass it through our network and we calculate the loss which we record. We also check how many of the answers were correct or matched with the actual or expected outcome, thereby giving us the accuracy which we record. So we are done with training of our model. Along the way, it had been printing the loss as observed on the training dataset. So now in cell number 9 and 10, let's plot the data that we have collected in terms of loss and accuracies. With the loss, we see that the training loss and the test loss has been decreasing with each epoch, and they both have been going hand in hand, which is good. On the accuracy front, our test set accuracy reached 100% after epoch 100, which is good. On the accuracy front, our test set accuracy reached 100% after epoch 100. So that's good accuracy. So that's how we train a model. I encourage you to go through this notebook and make changes and see the effects of those changes in the outcome of the training. So with this, we have now seen how to build a neural network using PyTorch. Next, we are going to see how we can save the same model that we have just trained now and save it to the disk and load it back for inferencing. So there are times when you want to persist your model state. You might want to do that to load it later for inferencing or for techniques like transfer learning. In cell number 11, the model state can be accessed via state_dict method, which provides a serialized version of your model parameters, the weights and the biases. This can be combined with torch.save to save it to disk in the PTH format. In cell 12, at a later time, you can use torch.load to read the model back. and then it can be passed to an empty or randomly initialized model to load back the weights. So let's try to do some inferencing on it now. In cell number 13, I have created a batch of one instance that I know is of type iris setosa. So the first thing I do is pass it through the network. And in cell 14, we collect the class scores calculated, and then I deduce the class by using the maximum class score and match it with the expected class. So they match. That's how you would save or persist in the state of a model. So this concludes this notebook, and next we will see the training. So this concludes this notebook, and next we will see the training of the neural network on a GPU. Now we'll be modifying the model which we have been training on the iris dataset, and we'll make it perform the training on a GPU. So for that, let's proceed to the notebook. We've been using this notebook to create the model and train it, and everything has been happening on the CPU by default, all the computations. In order to make it happen on the GPU, we need to make a couple of simple tweaks. So let's come here to cell number 7. The first thing I'll do here is I'll move the model to the GPU. When we create the model, all the sensors that it creates, the weights and biases are by default created on the CPU, and the way we move them to the GPU is invoke the .CUDA method. Then in cell 8, we'll inspect our training loop and look at all the tensors that we are creating and move them to GPU as well. So in the inner loop, where we iterate through the batches, we get the attributes and the actual classes in the form of tensors, and we move them to GPU as well. So you can see here that I've moved them to the GPU. And there are a few places down below where we handle the training dataset. We create a couple of tensors here and we move them to the GPU as well. Okay, so with those small changes, our model is now ready to be trained on the GPU. So once you run this, the training will start and all the computations are now happening on the GPU. Note that you will see a substantial change in the duration of the training between CPU and GPU only when you have substantial data which it needs to handle. Otherwise, in our case, for a lightweight data like the iris dataset, most of the time goes by moving the data from CPU to GPU and back, and so you won't find a substantial difference. We'll see this difference when we deal with images and text later on. So now we've come to the end of this section, and that was all about training a neural network on PyTorch. Now we've started by understanding what neurons are, what are the parts of neurons like weights and biases and the activation functions. We saw how they are coming together to form a fully connected multi-layer neural network, and we also built a neural network in PyTorch. We also looked at how data is to be loaded for training purposes, and then we focused on loss functions and saw what they do. We studied optimizers briefly and we studied their role. Then we went ahead and trained the neural network using a simple training loop, and we studied the accuracy and loss while doing so. Then we saw how to train a neural network onto the disk and load it back for inferencing. And we ended the section by looking at how we can tweak the model to have all the computations run on the GPU. So now it's time to start working on the MNIST dataset using PyTorch. So the fashion MNIST dataset is made up of images from fashion chain Zalando. It contains a training set of 60,000 images and a test set of 10,000 images. Each image is a 28 by 28 grayscale image associated with the labels from 10 classes. The fashion MNIST dataset is a drop-in replacement of the MNIST dataset, which contains a list of handwritten digits between 0 and 9. Each training and test example is assigned to one of the following labels. Label 0 refers to a t-shirt, label 1 refers to a trouser, and so on. Now let's head over to this notebook and get our hands dirty with this dataset. Now the purpose of this notebook is to familiarize yourself with the fashion MNIST dataset. Just so you know, the code below downloads the fashion MNIST dataset and trains a neural network so that it can distinguish between the different classes of the object. For now, I want you to get used to this dataset so you see what the results are. What do the different images in the dataset look like? I'm hoping that once you see the neural network work, you will want to know why it works. We'll walk through the code soon, but for now, just run the first 4 cells and train the neural network. Now coming here to cell 5, let's see how well it does on the images it hasn't seen before. You now have a choice of any 64 images to try this on. Pick any number between 0 and 63 inclusive and enter the number for the test image ID below. Now because the batch of test images is 64, you enter a number greater than 63 and you'll get an index out of bounds error. So I'm going to start off with test image ID 17, and when I run this cell, the neural network is predicting an image of a t-shirt. Let's confirm if that's the case. Now in cell number 7, we will display the image. I think I would agree that it looks like a shirt. So now what you can do is go back to cell number 5 and put in any number that you would like. So let's say for experiment purposes, you change the number to 52. Then you should rerun this cell and you should rerun this cell. Now coming to cell 7, when you run this cell, it's going to confirm that you will see that the image looks like a sandal. So you can go ahead and experiment with this number and other numbers until you are comfortable with being able to identify the different images in the fashion MNIST data. Does the model that we've created here seem to make any incorrect predictions for certain images? Can you find an example? Once you're done, let's work our way to understand how all of this fits together. Let's get a general intuition of our neural network problem and what we are trying to achieve. Then we'll get into the details of how everything works under the hood. So we start off with the original image, which is a 28 by 28 grayscale image, and as you can see, this is an image of an ankle boot. Now grayscale images have values between 0 and 255. The grid of numbers is a numeric representation of the 28 by 28 image. Now if you squint your eyes, you should be able to make out the image of the ankle boot in the grid of numbers. The zeros correspond to black, and the closer you get to 255, the wider the image is in that section. So we take the 28 by 28 image row by row and flatten it. So we are taking the first row and we then concatenate the second row. We then concatenate the third row to the first and second row, and so on. At the end of this flattening process, we have one long row which has 784 numbers. So let's get an overview of what our neural network looks like. So we'll start off with 784 input nodes, and each of these nodes correspond to a pixel of the image. We then have two hidden layers with 128 nodes and 64 nodes with ReLU. The final output layer has 10 nodes and uses the log Softmax function. Now remember that fashion MNIST dataset has 10 classes. So if you wanted to know the probability that the neural network predicts it's one of the different classes, you can just do an exponent to the log Softmax. So the higher the probability, the more likely the neural network predicts that the image belongs to the class of objects. The input layer needs to be 784 nodes because these are the number of pixels in the input image. Similarly, the output layer has to have 10 nodes because there are 10 classes in the fashion MNIST dataset. So why use 128 nodes and 64 nodes in the middle? Well, these are arbitrary numbers that I have selected. What if instead we used 784 nodes for the hidden layer 1 and for hidden layer 2? In a fully connected neural network, each node connects to every other node. So when we'll start to train our neural network, we adjust the weights or parameters from each node in one layer to another. This means for a network with 784 nodes for hidden layer 1 and hidden layer 2, we have almost 1.24 million parameters that have to be tracked. Let's look at the calculation for just the first section. The input layer has 784 nodes going into a hidden layer of 784 nodes. So the total number of weights is 784 times 784, which is 614656. Now each of the layers on the right will have one bias per node, and since there are 784 nodes in the hidden layer, there is an additional 784 nodes. So that's how we get a total of 615,440 nodes. Now our neural network is actually pretty small, so increasing the number of nodes per layer won't make PyTorch work significantly slower to make these calculations. You'll also find that there isn't a significant difference in the accuracy overall. Now another hyperparameter or option in your neural network is that you can try and adjust adding more hidden layers. So why only have 2? What if you have 5 or 10 or 20? Well, firstly, there is a trade-off calculation that you need to make. Are you getting much better accuracy for a neural network where you have millions more parameters and it takes longer to train? Now let's look at some of the terms you had in brackets. ReLU stands for Rectified Linear Unit, and it's a type of an activation function. So far, our layers have been linear functions. Now, if we had a whole load of linear functions, then we could just replace them all with a single linear function layer. Now, that's no good. The purpose of this activation function is to introduce some non-linearity into our model. So what do we mean by that? Now let's say we can plot 3 of the MNesh classes in 3D, just so we can visualize the problem. So let's plot all of the ankle boots, the sports shoes and sandals. Now if this was a linearly separable problem, then we could draw a couple of planes and the planes would separate each of the different classes. Now the problem is that some of the ankle boots look quite similar to the sports shoes and some of the sports shoes look quite similar to the sandals. So you will find that most problems are more complex than linear problems, and that is why we need nonlinear activation functions, because it allows the nodes to learn more complex structures in an image. So visually, this is what ReLU looks like, and mathematically it is defined as whichever value is greater, 0 or the value of x. The final layer that we have is a log softmax, so we are in a position to train our model to distinguish between the 10 different classes. Now if you wanted to determine the actual probability for each of the individual classes, you could just do an exponent to get the log softmax. Now if you are wondering why do we use log softmax as the final layer, well, we'll get into those details later on. Now when we create the class fmnest, instead of writing all new code, the new class is to be formed initially by inheriting the attributes and methods of a previously defined base class or superclass in PyTorch. This superclass is called nn.module. This means that our class fmnest is derived class or a subclass. What I can then do is, after inheriting the nn.module, I can customize it to meet my needs. In Python, object-oriented programming, whenever you create a new object, it initializes its data by calling the class's init method. Each new class you create can provide a init method that specifies how to initialize an object's data attributes. And when you call a method for specific object, Python implicitly passes a reference to that object as the method's first argument. For this reason, all the methods of a class must specify at least one parameter. By convention, most Python programmers call a method's first parameter self. So, a class method must use reference self to access the object's attributes and other methods. Now, because fmnest is a subclass of the nn.module, the first thing we need to do is, in the init method, we need to make a call to the nn.module's init method. We do that by using a call to the super function followed by the init. Next, you declare all the layers that you want to use. So this is the set of linear layers. So let's take a look at the first fully connected layer, or FC1 for short. It has 784 nodes going to 128 nodes, and FC2 has 128 as the input and 64 as the output, and so on. So let's dig a little bit deeper into what exactly nn.linear is doing. We have 784 inputs and they go into the 128 outputs in the hidden layer. So if we take a pixel 1 to start with, pixel 1 is multiplied with weight w1 and then a bias b1 is added. To start off with, weights w1 and the bias will be assigned a random value. So what nn.linear is doing is creating a linear transformation of the form wx plus b, and nn.linear automatically creates the weights and the biases and the bias tensors. The forward class in PyTorch is really important because this is where you define how your model is going to be run, from getting the input all the way to predicting which class the image belongs to. Now many of the methods that we used here, such as ReLU and Softmax, have already been implemented in PyTorch and are torch.nn.function, so we don't need to reinvent the wheel. In PyTorch nomenclature, you import torch.nn.functional as f. So how is the init class different from the forward method? In the init class, we have defined the fully connected layer FC1 as 784 nodes going into 128 nodes. Here in the forward method, we are defining the exact order of the different layers of the neural network model. So in the first line, we flatten the image so that it is 784 pixels long. We then provide as input 784 nodes to the fully connected linear layer, and this connects to 128 output nodes. We can then run this output through a ReLU function. FC2 has 128 input nodes and that goes to 64 output nodes, and so on. Now that we are done, we want to create an object of this mnest class that we've just created. In object-oriented programming, you can do that by declaring model is equal to fmnest. Now that we've had a high-level view of our neural network class, we take a look at the tensors, which are the building blocks of PyTorch. So let's get an intuitive understanding of what we are doing when training the neural network. What we do is to take the entire training dataset and divide them into batches. We then pass the batch of images with the labels to the neural network. In our example, this is a batch of 64 fashion mnest images from the 10 classes and labels. These labels state which class the images belong to. So let's take a look at one of these batches. The weights represented by W in the diagram contain information that the neural network has learned from the fashion mnest dataset that passes through. Initially, the weight matrices are filled with random values. This is our starting point. The weights are then gradually adjusted based on a feedback signal. So training a neural network is adjusting the value of these weights. So it's not only one batch of images and labels that would cause the weights to be adjusted, but all of the batches in the training dataset will result in an adjustment. One iteration over all the training data is called an epoch. At the beginning of the training and after one or two epochs, there is still progress to be made. The neural networks hasn't modeled all the patterns in the training data. You can see this because the average loss that we measure for each epoch continues to decrease. What you find is that after a certain number of iterations over the training data, the model starts to get good at learning patterns that are specific to the training data, but might not be relevant to new data. So the overall steps that we are taking in training are: take a batch of sample images and corresponding targets. We run this batch through neural networks to see what predictions the neural network provides. This is known as a forward pass. We then calculate the loss of the neural network for that batch. We do this by measuring the mismatch between the neural network predicted and the labels or the targets, which are the actual values. We then update the weights of the neural network so that it slightly reduces the loss of the batch. Let's take a look at this code so that we can see where we are doing this. We run only 3 epochs or 3 runs through the training data. You can increase this to 5, 10, 20, and you should see that the neural network continues to improve. I have kept it at 3 so you don't have to wait too long, and I found that the neural network is still reasonably accurate. Now the variable cumulative underscore loss, short for cumulative loss, is just a tracker for the total amount of loss for each of the batches. We then print out the average training loss at the end of each epoch. So we take a batch of images and the corresponding targets or labels from train loader. We also zero out gradients at the start of each epoch. We look at the gradients in a couple of minutes. We run this batch through the neural network to see what predictions the neural network provides, and we then calculate the loss of the neural network for that batch. This is measuring the mismatch between what the neural network predicted and which is stored in the variable output, and the labels or targets which are the actual values. And finally, we update the weights of the neural network. So the model that we've created isn't smart. It doesn't know what sports shoes are, or trainers, or ankle boots, and it can't tell the difference between them. So we take an image of an ankle boot as our input. It passes through our model and we get a prediction. Now what makes neural network special is that we can train it that whenever you provide an ankle boot as an input, it learns this. The way we do this is to train it with loads of ankle boot images so that it gets good at this. There's got to be some way where whenever we pass an image of ankle boots, it predicts ankle boots as the output. And when we pass it an image of a sports shoe, it predicts the sports shoe and not ankle boots or a bag or a dress as the output. This is known as loss function or a criterion. So a loss function takes an input, what the model predicts, and the actual correct output, and computes a value that estimates how far away the prediction is from the actual value. There are several different loss functions available by default from PyTorch. Now this table is really helpful to try and determine what loss function we should be using. When working with fashion MNIST dataset, we are working on a multi-class single label classification. This is because there are 10 classes and each of the images will only have one of the classes of images in it. So this means we need to use categorical cross entropy as our loss function, and Softmax should be the activation of the last layer. Now if you go to the PyTorch documentation and look under the loss function for cross entropy loss, it says this criterion combines nn.logSoftmax and nn.nll loss in one single class. Now nn.ll loss is negative log likelihood loss. Now this is an incredibly important statement and we'll find out why in a couple of minutes. So let's head over to see Softmax and see what's available to us there. And the Softmax documentation says it applies the Softmax function to an n-dimensional input tensor, rescaling them so that the elements of the n-dimensional output tensor lie in the range 0 to 1 and sum to 1. Now that's brilliant because that means the output tensor is the probability of that loss. Now there's an interesting note at the bottom of this documentation and it says this module doesn't work directly with negative log loss likelihood, which expects the log to be computed between the softmax and itself. Use log softmax instead. So we've seen that NLL loss referenced in the cross entropy section. So let's check out log softmax in this documentation. So log softmax applies the log of softmax function to an n-dimensional input tensor, and the log softmax formulation can be simplified as, and we have a formula there. Now the log softmax seems pretty useful. Now all we are after is the softmax function. So why can't we just use it and then do a log of it? Why all the fuss about combined log softmax function? Now this would be a fair question, and if we dig a little deeper into the PyTorch source code, we find some interesting comments. Now this comment is under the definition of the log softmax, and it says, while mathematically equivalent to log of softmax x, doing these two operations separately is slower and numerically unstable. This function uses an alternative formulation to compute the output and gradient correctly. So we could either use the cross entropy loss as our criterion, or we could use the NLL loss, the negative log likelihood loss. In terms of code, you specify either one of them as the criterion. However, when it comes to actually defining our neural networks, things are a little different. If you've decided to use the cross entropy loss as your loss function, then you don't need to use the log softmax activation in the final layer. You can see that the forward function doesn't have the log softmax function. This is because we learned earlier in PyTorch's implementation of cross entropy, this includes log softmax and the negative log likelihood loss function in one single class. The log softmax function is already done for you. If on the other hand, you have to use the negative log likelihood loss as your criterion, then we explicitly specify that the log softmax as the activation for the final layer. Now because I want to be explicit about each of the layers in the neural network, I have chosen to use the log likelihood loss and the log softmax combination in this section. So if you want to minimize the loss, then we need to adjust the parameters of the network. Now one of the things that we do have control over are the weights shown as W in this diagram. So our goal is to try and determine some way to adjust the weights so that the loss is minimized. And if the loss is minimized, then our prediction and actual value will be closer together and our model will be more accurate. We do this by using a process called gradient descent. PyTorch does this using AutoGrad, and we look at this next. Now let's say the vertical axis in the diagram represents our loss function and the other axis are model parameters. So weight 1 and weight 2. So we start at the uppermost point of the black line and our goal is to get minimum of the loss function. And we do that by making calculations and finally ending up at the bottom of the black line. If you have taken calculus, it's a really helpful tool to help us find the minimum or the lowest point of a function. Now, it so happens that the loss function is differentiable, so this means we can compute the gradient of the loss with regards to the weights of the model. The challenge that we have is that every weight coefficient in your network will have its own dimension. Now, in a typical neural network, there are thousands if not millions of coefficients. This means very quickly it can become a computationally challenging problem. This is where the magic of PyTorch's AutoGrad comes in. It takes away the complicated mathematics of having to calculate the gradient for multiple dimensions and automatically does it for you in a computationally efficient way. In the forward pass, we calculate the loss. In the backward pass, we calculate the gradient of the loss with respect to each of the weights. So let's head over to the notebook, and you must be familiar with the first two cells over here. We are just importing libraries and we are downloading the fashion MNIST training and test dataset. And now I'm quickly going to scroll up to cell number 4. So another way to represent the same network is to use PyTorch's NN sequential. So instead of using classes in cell 4, I'm defining the exactly same neural network by using nn.sequential. So as you can see, the model is equal to the MNIST in cell 3. And that has been commented out, and the reason I'm doing that is because I want to show you the weights for some of the layers. So this way in cell 4 I can see what is my first layer by indexing. Now the class-based method of defining a neural network doesn't support this. So the first layer is model 0. So model 0, then you can see that this corresponds to the first line here with input features of 784 and output features of 128. And I can do exactly the same thing and see that the next layer is actually ReLU and so on. So in cell 5, let's take a batch of samples with the labels. So that's 64 images and labels. And in cell 6, let's define the criterion as negative log loss likelihood. And in cell 7, now let's print out the weights for the first layer. So these should be random values, and let's print out the initial weights, and because I want the initial weights of the first layer, I say model of 0.weight, and you can see that these are random values that have been generated for the weights for the first layer. Now because we haven't done a backward pass, there shouldn't be any gradients yet. So let's confirm that this is the case, and in cell 8, to do that we do model of 0.weight.grad, that is the initial weight gradients, and you can see that there is none. So in cell number 9, now let's do a forward pass and calculate the loss and then do a backward pass, and you can see that the weights are exactly the same, but now the gradients have been automatically calculated. Now this is done by AutoGrad. Now just for the first layer, that is a tensor of 784 by 128 gradients that have been calculated on the fly. Now you can check out some of the other linear layers and the gradients calculated by AutoGrad. So activation functions such as ReLU don't have any weights associated with them. Their role is to add nonlinearity to the network. So model 1 is our ReLU function, and you can see that there are no weight values associated with model 1. In the same way, model 2 is our linear function, and you can see that there are weights associated with layer 2 and there are gradients associated with that layer. So now let's head over to the AutoGrad with Tensors notebook, and we are going to do a lot of stuff from scratch here. So remember that AutoGrad is used for automatically calculating the gradients of tensors. Now AutoGrad works by keeping track of operations performed on tensors and then going backwards through these operations, calculating gradients along the way. And to make sure that PyTorch keeps track of operations on a tensor and calculates the gradients, you need to set the requires underscore grad equals true on a tensor. So you can do this when you create your tensor with the requires grad keyword. So in cell 1 we import torch, then in cell 2 we create our tensor W from the normal random distribution. Then in cell 2 we create our tensor W from the normal distribution. So rand n with the dimensions 4 by 3, and then we use requires grad keyword. In cell 3 we print out the value of W, and you can also set the requires grad to true elsewhere. So in cell 4 I'll first turn the tracking off by setting it to false, and then we'll set it to true again. So I can say W requires grad and false, and you can take a look at the value of W now. So in cell 5 let's turn that back on. So we do W dot requires grad true. Now in cell 6 let's create a new tensor y, and let's say y equals torch and the exponent of W, right? So let's just print out the value of y over here. So we print y, and you can see that y is an exponent operation because you can see that y is torch e raised to the W. Now in cell 7 if I print the gradient function of y, so that's print y dot gradient function. The AutoGrad module keeps track of these operations and it knows how to calculate the gradient for each one. In cell 8 if we define another operation to get scalar value, so let's call that tensor out p. So out p equals y dot mean, and I print the value of out p. Now in cell 9 if we check the gradients of W, we'll find that they are currently empty. So print W dot grad, and we find that it has a value of none. Now that's because we haven't run the backward function yet. Now in cell 10 when we call backward on the output tensor, that's when the gradients are calculated. So out p dot backward, and then we run the cell. Now this calculates the gradient of out p with respect to grad. So in cell 11 I am going to print out the value of the gradients of W again. So print W dot grad, and you can see that AutoGrad has automatically calculated the gradients for W. Now coming to cell 12, to stop a tensor from tracking history, you can call the detach method to detach it from the computation history and to prevent future computations from being tracked. So I can do a print w.detach, and the gradients for this tensor will not be updated. Just so you know, you might want to prevent tracking history when you want to evaluate a model because the model may have trainable parameters. So that's when you have the requires grad flags set to true. But for whatever reason, you don't need the gradients calculated. So in cell 3, I do a print out p requires grad, and you can see that the value is equal to true. Now in cell 14, if I use with torch.noGrad block, so that's with torch no grad, and I say out p is equal to, let's say, w plus x, you get the mean of that, and then I print out p requires grad. Now of course some of you would have noticed that I haven't defined x before, but I have defined y, so I'm going to change that x to y, and you can see that within that torch.noGrad block we prevent tracking the history. So in the next section we will look at optimizers. So now that you have defined your network architecture and the loss function, the job of the optimizer is to determine how the network will be updated based on the loss function. So the optimizer uses the loss values to update the network's weight. It implements a variant of stochastic gradient or SGD. Now PyTorch makes working with an optimizer pretty straightforward with torch.optim package. Most of the commonly used methods are already supported. Before we look at torch.optim, let's take a look at the training steps. So we take a batch of training samples and corresponding targets. We run a forward pass through the network on the sample to obtain predictions. We then calculate the loss of the network for the batch. So that's a measure of the mismatch between the predicted values and the target. We then perform a backward pass and compute the gradients of the loss with respect to the network's parameters. And finally, we reduce the loss by the batch by taking a step of the optimizer. And this updates the weights of the parameters using the previous weight of the parameter and then subtracting the learning rate multiplied by the gradient of the loss with respect to the weight. Now, one really important thing to remember here is that when using PyTorch, we should zero out the gradients. Now, if you think of a single weight in your network, remember, if you think through the steps that we are trying to achieve, we run a forward pass, calculate the loss, do a backward pass, compute the gradient of the loss with respect to the weight. You would only want to update the weight by an amount given by the optimizer for that batch. Any updates to the weight for any other batch are meaningless. By default, when you do multiple backward passes with the same parameters, the gradients are accumulated. So this means for each batch of data, you will want to zero out the gradients using optimizer.zero_grad. So let's see the optimizer notebook and let's run through the first couple of cells as per normal. So let's directly jump on to cell 6 where we import the optimizer. So here in cell 6 we import optim from torch. So what we are doing here is we have defined the criterion and the optimizer, but we won't use it yet. So here LR corresponds to the learning rate, and in cell number 7 let's do a forward pass, calculate the loss and then do a backward pass. So we've calculated the weights and the gradient here. And now in cell number 8 let's go ahead and update the weights using the step function of the optimizer. So that's the optimizer.step. Now in cell 9 let's go ahead and run the next bit of code, and you can see here that the weights have been updated ever so slightly. So in cell 7 output, in the third row for example, the last entry is around 0.0315, and after running the optimizer we see that the weights have been updated to 0.0314. So now that we've updated the weights, we don't want to accumulate the gradients. So in cell number 10, let's zero them out using the optimizer.zeroGrad, and in cell 11 we can see that we've got the updated weights but all of the gradients have been zeroed out. Now in cell number 12 what we want to do is put that through a loop. So I'm going to do a couple of things first just to make sure that the code looks like what you've seen before. Now as we've demoed what happens at each of the layers, we don't need nn.sequential anymore. So let's go back to our classes method. So we instantiate our fmnest class by doing a models equal fmnest, and we have the number of epochs set to 1. And now I want to see the loss for each batch. So we have batch num variable and we print out the loss per iteration. So batch num is equal to 0. So I have print batch number, what I've just defined, and then the loss and the loss item. And in the for loop we use the enumerate function to track the number of batches. If I want to enumerate the number of batches with a train loader 1, then I also need to specify that's going to be stored in batch_num, and my images and labels is stored in a tuple. So once we run this cell, and so you can see that we've run one epoch. Now where does this number 938 come from? Well, remember that the training dataset has 60,000 images and we are dividing it into 64 batches. So this means that we have 60,000 divided by 64. So this gives us 937.5. So that's where you get 938 batches, and the final number that you see beside the training loss is the average loss for all of the batches. Now one of the huge benefits of PyTorch is that you can easily troubleshoot your network using regular Python debuggers. If you haven't used a Python debugger before, it's very easy to do so. Here are the main commands that you need. If you want to enter at a specific point to the code, then you can use the set_trace method after importing it from the core.debugger module. You can execute the current line of code and move on to the next line by typing n for next. If you have multiple functions and you want to follow the logic of your program across several functions, then step or S is what you want. It can become very easy to not be able to see the wood for the trees. So the list command or L helps to provide context of which line you are at. You can also print out the values of variables and perform other Python operations in the debugger. You can hit enter to repeat the last command, and this is particularly useful when you are just scrolling through some lines of code, line by line, with the next, and finally it's a cue to quit. So let's head over to the troubleshooting notebook. So I've made a small change to the Python class file, and so let's see if we can try and figure out what the change is and if there is a problem. So let's run the first couple of cells as normal, and then we run the cell number 3. Now where we run cell 4, we can see that we've got a problem with the code here. So it looks like there seems to be a problem here, and so in cell number 5, let's import the setTrace method. So from ipython.core.debugger import set_trace. So we import this function here, and let's run this bit of code here. So if we look at the code, we expect the images and the labels should be populated from the train loader. So let's check that is the case, and let's look at the images and the labels. So I can print out the actual value of the images and labels, and you can see that I've got both the images and labels, so no problem here. Now what Python type are the images on the labels? Let's find out. So type images, so that's class torch.tensor, and we'll do type labels, and that's a class torch.tensor2. So this should come as no surprise that the images are tensors. Now if you want to get the sense of the context and where we are in the code, you can type in L for list to see that where we are at. So an L and enter, and now you can see that we are just about to run the optimizer.grad function. So let's move on by typing N for next, and let's do a forward pass through the model. So I'm going to type in N, and then let's print out the value of the output. So print output. Now that's odd, because we should have received the prediction from our model. Instead, we've got nothing back. So let's get out of the debugger by typing Q for quit, and let's head over to the forward method within our class. So we are heading over to the cell 3 of our notebook, and now we take in our input image here, we pass it through a linear layer and run a ReLU. We then take the output of that as our input to the next linear layer and pass it through a ReLU activation, and finally we pass it through the third linear layer and pass it through a log softmax. So everything from the model looks good. What is missing is that we don't return the output of x at the end of the function. So let's change that and see if it fixes our problem. Now let's rerun this cell number 4 after making change to the forward method, and you will see that we'll get the training losses. So our model has completed training, and it seems that return x was the problem in our model in our class definition. So now moving on, let's comment out the code in cell number 5. So we have commented this, and now let's just run through the rest of the code to make sure that we don't have any additional problems. So let's just run through this, and we see that we've got an ankle boot here, and the rest of the code seems to run error free. So you can see that the Python debugger is a huge help for troubleshooting, and it's one of the many reasons why PyTorch is so popular today. Now when training models in deep learning, we'll often use GPUs. Now GPUs, or graphical processing units, are not replacement for CPU architecture. Rather, they are powerful accelerators for existing infrastructure. GPU accelerated computing offloads compute-intensive portions of the applications to the GPU, while the remainder of the code still runs on the CPU. One way to think of it is CPUs are for general purpose computing and GPUs are great for intensive computational calculations such as matrix multiplication, which we use as part of training a neural network. Now, training PyTorch neural network on a GPU is pretty easy. Fortunately for us, Google Colab gives us access to a GPU for free. So, we'll head over to the notebook in a few minutes to see how to do this. CUDA is a parallel computing platform and programming model developed by NVIDIA for general computing with its own GPUs. When using GPUs, there are three things that you want to do. At the top of the notebook, specify the CUDA device. Secondly, you want to do transfer from the neural network to the GPU. And finally, you want to send all of the inputs and the targets to the GPU. So now let's head over to this notebook to see how do we do this. So what you can do is run this notebook in Google Colab. You can select upload, choose file, and you can grab the CPU to GPU notebook. And there are two ways to make our notebook run on GPUs. You can select edit, go to the notebook settings, and then change the hardware accelerator type from none, which is a CPU based solution, to GPU. Or the other option is you have to select at runtime, change the runtime type, and again at the hardware accelerator drop down menu select GPU and then save it. So after running the first cell in cell number 2, the first thing that we want to do is at the top of the notebook to add a cell and specify the CUDA device. So I can say device equals torch.device and it's CUDA if torch.CUDA is available, else we have a CPU device, and then I just want to print this device, and you can see that we have access to a CUDA device or a GPU here. Now in cell number 3, to download the fashion MNIST data, as we've done in the past, we can define our fashion MNIST class as normal. Now the next thing we want to do is transfer our neural network, which is the fMNIST, to the GPU. So what we can do is we can move the model from CPU memory to GPU memory. These methods will recursively go over all the modules and convert their parameters and buffers to CUDA tensor. So in cell number 5, I say model.to and then I move it to my GPU memory by saying model to device. Now because I have sent my model to GPU memory, I also need to send the inputs and the targets at every step to the GPU. So in cell number 6, you load the images and the labels from the train loader and send them to GPU memory. So I say images is equal to images and then to my GPU. And I exactly do the same thing for the labels. So labels is equal to labels.to device. Now that we've got both the images and labels in our GPU memory and our model is in GPU memory, we are in a position to train our network. Now what you will find is that when we are training, we want to be using GPU memory. When we are testing, we want to be using the CPUs. So we need to copy the model over from the GPU memory to the CPU. Now we don't need to do anything to the inputs as the test loader is by default on the CPU memory. So what we did in the training step was to take the training images and the labels and then move them across to the GPU memory. In the real world, you will find that we train on GPUs, but when it comes to deploying the model, say on a CCTV camera, then having a GPU is too expensive and we normally would have a CPU and we run our model on that. So in cell number 7, because we are going to be actually testing our model, I am going to be moving our model back to the CPU memory. So I say model.toCPU and I should be able to run the next few cells as per normal. So the prediction is ankle boot, and I think you'll agree with me that it looks like an ankle boot. Now coming here to cell number 13, let's see what error message we get if we actually have the MNIST model on GPU and our input and our labels on the CPU memory. So I'm going to transfer my model back to the GPU memory, so model.toDevice, and then I'm going to comment out this line of the code. So the models on the GPU memory and the test labels and the test images are going to be on the CPU memory. And you can see that I get an error message that says runtime error. Expected object of backend CUDA but got backend CPU for argument. So this is the error message over here, and it's really important to remember to keep both your models and your inputs on the same type of memory. So let's fix this. So now in cell number 14, we know that the images and the labels are on CPU memory. So we'll move our model back to the CPU memory here. And we uncomment model.to CPU. And then we are back to a working solution. So now up to this point, we haven't quantitatively defined how accurate our model is. I mean, the model seems to be accurate for most of the images that we've looked at. But how does it do against all of the 10,000 test images, for example? So let's check this out in our validation notebook. And now we are pretty familiar with the first bit of code. So I'm just going to run through that. We get as far as training our model, and you're familiar with the next bit of code where we are making the predictions. So we are pretty familiar with all of the code up to this point. So I've added a chunk of code to get a definitive answer of how the model that we've trained with only 3 epochs of training data works with the test data, and I'll walk you through it. So we directly come here to cell number 10. Now firstly, we don't need to calculate any gradients. So let's do all this code within a torch no-grad clause. We can use the numCorrect variable to store where the predictions match the labels, and the total variable will track the number of images that we are testing. We'll use this a little later. So we get the images and the labels from the test loader, and then what we want to do next is a forward pass through the model, and the predictions are stored in log ps. Now remember that these are log values, so we need to use the exponent if we want to convert to a probability. Now we just want to make sure that everything's running okay for this batch of code. So I'll just quit after one pass by setting the condition if count is greater than 0, break. Now in the output here, each of these lines correspond to the probability that the network predicts it's one of these classes. So coming here to cell 11, if you want the class with the highest probability, all we need to do is grab the index with the highest value using a function like argmax, and what we'll do is keep a track of all the images using the total variable. Now coming to cell 12, if you look at the last couple of entries for the predictions and the labels, you can see that they are almost identical. So that's displaying what's in the tensor, pred and labels. So in cell number 13, we can compare the entire predictions and labels and where they are same. So we'll get a value of 1, and where they are not, we'll get a value of 0, that is false. So in cell number 14, that's why we can use the pred equals labels and then do a dot sum to get the total number of correct entries. The item function that we've stuck onto the end gives you a number from a tensor containing a single value. And finally, in the last line, we can print the percentage accuracy as being the number of correct divided by the number of total labels. And you can see that the accuracy of the model for 10,000 images is approximately 82%. Now in this notebook PyTorch playground, I've provided you with all of the code that you're familiar with, and then I've started experimenting with adding a couple of changes. So instead of training with 3 epochs with a GPU, I've trained a model for 30 epochs. Now just a word of warning, it's going to take a little bit longer to train obviously, and it might take around like 10 minutes. So a couple of questions for you. Do you get a more accurate model as a result of training with more epochs? I've also created several plots that you can see how your model is going to do for the training loss, test loss and the accuracy over 30 epochs. This way you can make changes and visually see the difference that it makes to the accuracy of your models. Now there are a couple of things that I'd like you to experiment with. So can you get better accuracy from training the model if, for example, you add more layers? So you need to change some of the code that we have at the top. Or can you change the number of nodes in the layers? Again, you've got to make some changes to the fashion mnist class or train over few or higher epochs. And then can you improve on your results if you add additional layers like dropout? Don't know what dropout is? Well, you can look it up using this link that I've provided and see what changes you need to make to the code to implement it. So with this, we end our lecture over here.